In the previous model, we learned a little bit about risk prediction and how to construct an ROC curve in STATA by using a line graph. Now in this module, we're going to think about how to compare different risk prediction models, and in doing that, we're going to learn about how to make some more sophisticated graphs within STATA. So in practice, if we think about the previous model that we used, for a risk prediction model, it would be easier if we didn't have to measure very many things to decide whether a patient is high or low risk when it comes to their probability of getting CHD during their lifetime. So, in order to evaluate the previous model, which contained a bunch of factors, we're going to now come up with a new model that only contains blood pressure. It's going to contain systolic and diastolic blood pressure as well as sex. And then we're going to compare Model 1, which was the original model with lots of factors, and Model 2, this new model with only a few things in it, and we're going to see which model provides the better prediction model. So now open up the ROC.dta dataset within STATA. Once you have the dataset open, go to the data browser. In the previous model, we only used the information corresponding to Model 1. Now we're going to look at the information for both models. So for a given probability cutoff, if you are confused as to what that is, see the previous model, we have sensitivity, specificity, and false positive rate for Model 1, and then we have sensitivity, specificity, and false positive rate for Model 2. So what we're going to do is we're going to construct a graph that contains on the x-axis for Model 1, the false positive rate, and on the y-axis, the sensitivity. And then on that same graph, we're going to overlay on the x-axis false positive rate versus sensitivity on the y-axis for Model 2. So this is going to be a relatively sophisticated graph. To make this graph, we go Graphics, Two-Way Graph, Create. So the first thing we want to do is make the exact same line plot that we made in the previous module with sensitivity versus false positive rate for Model 1. Hit Accept once you have that, and now we have one plot definition in this window. Let's create another one. So now again we want a line plot, but on the y-axis we're going to have sensitivity for Model 2, and on the x-axis false positive rate for Model 2, and hit Accept. I want one more line on this plot, so I do line plot. On the y-axis I want C, and on the x-axis I want C. So that's the cutoff, and what that's going to do is it's going to create an x equals y line, and we'll see why we want that later. So hit Accept, hit Submit, and you now see that we have two ROC curves and our one x equals y line. Now going back to our plot definitions, go to plot 1 and hit Edit. If we wanted to see exactly what points are being plotted on our graph, instead of doing a line plot, we would say we want a connected graph. So change plots 1 and plot 2 to be connected graphs. Hit Submit, and now you see that the exact points that are being plotted now appear on the graph. So within STATA, you can see that there's a legend down at the bottom, but this legend doesn't really look exactly like we would want it to look. Further, it would be nice if we had our x and y axes labeled. So let's go into the graph editor and let's make our graph look exactly like we want it to. So double click on this legend, and instead of saying sensitivity Model 1, change it to just say Model 1. Similarly for Model 2. And then highlight probability cutoff, right click, and hide. Same thing for the line, right click and hide. So now in your legend, all you have is you can distinguish between which line represents Model 1 and which line represents Model 2. Now let's add labels to our axes by going to y-axis 1 and double click on title. Recall that on the y-axis we've plotted sensitivity. On the x-axis, we've plotted the false positive rate. So now we have a graph that looks more like we would want it to. We can add a title that says ROC curve. Now why did I plot this line that corresponds to x equals y? Essentially what this corresponds to is a false positive rate that's exactly equal to sensitivity. So this is what I call the coin flip line, where you have a 50-50 chance of being diagnosed as high risk versus low risk, regardless of what your prognostic factors look like. So this x equals y line corresponds to a prediction rule that doesn't take into account any prognostic factors. On the other hand, we have Model 1 and Model 2 that do take into account prognostic factors, and we're going to evaluate which does better. Now, I'm going to tell you that using this ROC curve, I know that Model 1 is outperforming Model 2. Now, how can I tell this from the ROC curve? Well, the curve for Model 1 is above the Model 2 curve. This implies that for any false positive rate between 0 and 1, the sensitivity is higher for Model 1 versus Model 2. Now, that's not necessarily always true because there's this little blip here, but in the regions where the false positive rate is reasonable, Model 1 is always outperforming Model 2. By including these additional covariates in Model 1, we can improve our ability to predict high versus low risk patients. Now, you're the doctor statistician though, so you have to make a decision as to which model you would recommend. Do you prefer Model 1 or Model 2? So to think through this process, we know that Model 1 is more complicated. It requires measuring more outcomes. However, we have to balance in practice cost with the added precision. Now in this case, the additional covariates that we're measuring might not be too expensive, such as BMI, cigarettes, cholesterol, and I might choose Model 1 as the doctor statistician. But in practice, people are using these ROC curves to evaluate different genetic risk factors and new biomarkers, so if these are expensive, we need to balance cost with added precision, and ROC curves can help us learn about how much added precision we're actually getting in this setting. Now, later in this course, we're going to learn how to actually come up with these predicted risks, and these are used very frequently in practice. So as I said previously, risk prediction is a hot topic right now in biostatistics and epidemiology. There's a paper that I found just using Google Scholar that comes up with a risk prediction model for coronary heart disease, and it's based on Framingham data, and it has 4,872 citations. So, as I said, these are very frequently used in practice. It's good for you to know about, as well as we've learned how to make some very complex graphs that overlay lines within STATA.